This video is part of the series to accompany discrete mathematics and functional programming. I'm Thomas Van Drunen. This video is the second in a two-video sequence that introduces writing operations and types in ML. In the previous video, we looked at some beginning examples of writing functions, that is defining one's own operations, and writing data types, that is designing new types. What I want to do in this video is give you a first experience in dealing with definitions that are self-referential. This complements the previous video in that I will give you a few more examples of functions and data types, except that this time those functions and data types will be self-referential. And something that is defined in terms of itself is called recursive. And I'll start with the story of probably my earliest memory of a recursive definition. In fourth grade sometime, in reading class, we had a story that involved something about kids playing at the beach. Exact details are lost to memory at this point. But somewhere in the story, the word coral came up. And coral was listed in the reader, in the list of vocab words at the end of the story, and for words like that, our teacher required that we would look the words up in the vocabulary at the end of the reader and write out the definitions to turn in. In some cases, there would be more than one definition for a word, and in those cases, we needed to choose which was the correct one based on the context in which it was used. There were two definitions of coral in my fourth grade reader, and they weren't too far off from the first two definitions you'll find in Merriam-Webster today. First definition, a calcareous or horny skeletal deposit produced by anthozoan or rarely hydrozoan polyps, especially a richly red precious coral secreted by Gorgonian, genus Corallium, polyp or polyp colony together with its membranes and skeletons. Or, second definition, a piece of coral, and especially of red coral. I chose to write out the second definition. Even if it wasn't the right one in context, it was less to write out. I probably wouldn't have remembered that story, except that some years later another teacher dinged me for trying to define a word using the very word I had to define. You can't use a word in its definition. You sure can use a word in its own definition. The dictionary does. You just need to know what you're doing. As I mentioned in a previous video, a fundamental goal of a course like this is to make recursion and recursive thinking seem natural. Recursion is something that any programmer, regardless of style or programming language, needs to be able to understand and be able to use. It is especially important in functional programming because in functional programming, recursion is the natural way to do things. It's an essential part of the natural way to do things. But I'm interested in teaching recursion not merely because it's useful, but also because recursion is beautiful. I'm not so much using recursion so that you'll know how to write better ML programs, so that you'll better be able to write programs in ML. Instead, I'm using some ML examples, and some pretty basic ones at that, so that I can teach you some of the first lessons of recursion and recursive thinking. And it's not the facts of recursion that I'm so interested in introducing to you. Rather, I'm more interested in helping you to think recursively, and that's going to take some time and practice on your part. Our first example is a cliché for introducing recursion, but there's a reason almost everyone uses this example. It's simple, and it makes the point. You may recall that the factorial of a natural number is defined as the product of that number and all the natural numbers less than it. Because it is useful mathematically, the factorial of 0 is defined to be 1. Here are some examples. A recursive definition of factorial can be built from the following observations. The derivation of 5 factorial contains the entire derivation of 4 factorial. We can substitute 4 factorial in for it in the derivation of 5 factorial. Likewise, a derivation of 4 factorial contains that of 3 factorial. Another substitution. The pattern happens again between 3 factorial and 2 factorial. When comparing 2 factorial and 1 factorial, it may seem silly to make the same substitution, but the point is, the pattern still holds at the trivial cases. In fact, we have the same pattern, again trivially, between 1 factorial and 0 factorial, since multiplying by 0 factorial, that is 1, doesn't change anything. We can take this observation and generalize it to the following formula. N factorial is n times n minus 1 factorial if n is greater than 0. For n equals 0, n factorial is 1. Now we have defined factorial in terms of itself. Things to notice. A recursive definition like this needs to have at least 2 parts, as we can see here in the brackets and condition. In addition to the part of the definition that is self-referential, which we call the recursive case, there must also be a part that is not self-referential, the base case. There needs to be a starting place that the self-referential part of the definition depends on. This is true also of the dictionary's definition of choral. The first definition is the base case of sorts. The second is the recursive case. Now the big news for us is that we can replicate what's going on in this formula perfectly in ML using pattern matching. I've changed the order here. I'm putting the 0, the base case, first, and the n case, the recursive case, second. But we can see that that first pattern, fun factorial 0 equals 1, corresponds exactly to the base case in the mathematical definition of factorial. The second rule, for factorial of n, where n is something other than 0, corresponds to the recursive case in the mathematical definition. And in fact, when we talk about recursive functions like this in ML, we use the same terminology, base case and recursive case. So functions can refer to themselves. How does it work? Watch this. When the ML interpreter evaluates something like factorial of 5, it applies the rule, the recursive rule, in our definition of the factorial function, to essentially substitute factorial of 5 with the expression 5 times factorial of 5 minus 1. That, of course, is 5 times factorial of 4, but now the ML interpreter needs to evaluate, that is, apply the function factorial to the value 4. Factorial of 4, then, following that recursive rule, is 4 times factorial of 4 minus 1. This leads to a call of factorial of 3. Now looking back at this point, notice that the calls of factorial of 4 and factorial of 5 are essentially put on hold until the result of factorial of 3 can be computed. The application of factorial to 3 in turn requires application of factorial to 2. This leads to the call factorial of 1. Finally, we get to factorial of 0, but here the base case applies, and the result is 1 immediately. Now factorial of 0 is replaced by 1 in the body of the call factorial of 1. The result of that is, again, 1, and that result then is used in completing the evaluation of the body of factorial of 2. 2 is the result of factorial of 2, so the call factorial of 3 is now evaluated with 3 times 2. We now have our result of factorial of 3, and so 4 times factorial of 3 can be evaluated, that is 4 times 6. 24 is the result of factorial of 4, and finally we are back to our original call, factorial of 5. And we can evaluate that to get 120. That's the only example I'm going to give you today involving numbers. But you can see others in the exercises of section 1.12. A better way to illustrate this idea of self-reference for now is to notice that not only algorithms can be recursive, but data can be structured recursively as well. This next topic that we're going to talk about briefly isn't covered in the book until Chapter 6, but perhaps you'll find this quick look ahead to be useful at this point. So imagine you're a programmer at the Recursive Open Face Sandwich Shop, the ROFSS. ROFS has an idiosyncratic way of defining what a sandwich is. So first of all, a slice of bread by itself is a sandwich, even though you could say it's a trivial sandwich. Second, any sandwich can be used as the basis for another sandwich. That is, you can make a sandwich by taking another smaller sandwich and adding a new ingredient on top of it. Suppose we have these ingredients. Now here's our definition of a sandwich. A sandwich is either a slice of bread by itself, or it is a layer of an ingredient upon another sandwich. Notice that this second pattern contains a tuple with the added ingredient and the inner, smaller sandwich. So in this way, we can make larger and larger sandwiches by adding more ingredients to the previous sandwich that we have made. Just as a side note, when you see in the ML interpreter has the pound sign as the innermost part, the pound sign here simply indicates that there is more of this value that could be shown, but the ML interpreter is truncating the representation of this value simply for the sake of space to reduce clutter. So if we wanted a complete display of the contents of the sandwich, what we would need to do is write our own function that will turn a sandwich into a string. Finally, we can write operations on the sandwich type. The operations will be recursive, and they will be defined recursively in the structure of the data type itself. Suppose we wanted to count the number of ingredients in a given sandwich. Remember that bread doesn't count as an ingredient per se. So the number of ingredients in a sandwich that is just a slice of bread is 0. For a layer with ingredient X and inner sandwich S, the number of ingredients is 1 plus however many ingredients the inner sandwich has. Note the type. This function takes a sandwich and returns an int. Now suppose we wanted to transform a sandwich by removing all layers of cheese, so as to make it appropriate to someone who's lactose intolerant. Let's write a function, remove cheese. To remove cheese from a slice of bread, we return it unchanged. It is already cheese-free. What if this function is given a sandwich that is a layer of cheese upon an inner sandwich, S? Notice how we're using pattern matching here. The pattern is any sandwich that is a layer, that is not just a slice of bread, with the specific ingredient cheese on that top layer, and any sandwich, call it S, below. S is a variable. Cheese is a constant. And in this case, what we want to do is remove the cheese of the inner sandwich S. The sandwich, like the one we're given, except without cheese, is just like the inner sandwich if all of the cheese were removed. In other words, we remove the top layer of cheese and we remove any other layers of cheese the inner sandwich has. If we're given a layer with some other ingredient X, which can't be cheese because the previous rule catches cheese layers, Then we keep that layer with ingredient X unchanged, but we transform the inner sandwich with the recursive call to remove cheese. This is a very tall sandwich and a very cheesy sandwich too. In this example, I need to count my parentheses very carefully. Hopefully I've gotten them all. Looks like it. And although it does not print out the entire sandwich, you can see that we have removed the cheese. Note the type of the function remove cheese. Given a sandwich, return another sandwich. As with the other videos, I don't expect someone to be able to watch this and suddenly have mastered all the things that we've talked about. You won't understand recursion until you've worked with and seen some more examples, and especially have practiced this yourself in writing recursive functions and finding recursive solutions to programming problems. But that's worked into the rest of this course, especially in the exercises. One of the most important tools we'll have for practicing recursive algorithms and practicing recursive thinking to devise recursive algorithms is the list construct in ML. And lists are the subject of Chapter 2, and I'll talk through some of those concepts and also talk through some of the examples in the next few videos.